Hello everyone. Today I would like to introduce our work, TP-TIO, a robust thermal-inertial odometry with deep thermal point. I would like to introduce our work from 5 aspects: the motivation, related work, algorithm, experiments, and conclusion. In recent years, there are increased demands for mobile robots to achieve robust post-estimation in challenging environments such as fog, storm, snow, smoke, and dust environments. However, most of visual and laser odometry will degenerate in such obscure scenarios. Compared with laser and visual sensor, thermal camera can provide more useful information in obscure environments. Here are 3 figures illustrating the observation of laser scanner, visual camera, and thermal camera in the same smoke environment. We can clearly see that the observation of laser scanner and visual camera are degenerated. In contrast, the infrared ray of thermal camera can penetrate the smoke and provide the details of the room, which is beyond the human eyes. For specific demand, our thermal-inertial odometry is developed in the context of DARPA Subterranean Challenge, which will help our robot to navigate in fog environments. However, compared with visual images, the data from thermal camera is quite noisy. Since thermal images have fixed pattern noise and low signal-to-noise ratio, the thermal images are low contrast, which brings difficulty for feature extraction and tracking. Also, because of NUC phenomenon on thermal cameras, the data of thermal camera will be interrupted at a certain rate, which brings difficulty for odometry. Thirdly, since our thermal odometry will be implemented on an onboard system, we have high requirement for real-time performance. Here, I would like to introduce some related works about feature extraction and thermal odometry. For classical feature extraction methods, such as Harris, Orb, SURF, SIFT, and etc., we found that these methods are not robust enough to overcome severe image transformations, such as viewpoint changes, blurring, and noise. For learning-based feature extraction methods, such as superpoint, superglue, and etc., these methods are mainly designed for visual images. For thermal odometry methods, we found that these methods heavily rely on the quality of thermal images, which is hard to guarantee. Motivated by the discussion above, we propose a novel deep thermal-inertial odometry, TP-TIO. We will present our work into 4 parts to illustrate the main ideas. The first one is training process. To detect features robustly on noisy thermal images, we propose a new training process which uses noise reduction and pseudo-feature supervision strategies. Then, we propose a new ThermalPoint network. It has a shared encoder which abstracts high-level features and reduces the dimensionality from the input image. After that, the architecture is divided into 2 task decoders: feature detection decoder and descriptor decoder. To improve real-time performance, the descriptor decoder is only used in training process and will not be used in interfacing process. Instead, we use radiometric feature tracking method to establish feature correspondences. Finally, we use thermal-inertial bundle adjustment to obtain the post-estimation. Let's introduce our first contribution, ThermalPoint. ThermalPoint network is based on the famous SuperPoint network. However, there are some limitations that needs to be solved when performing on thermal images. Firstly, SuperPoint is only designed for visible images. Secondly, SuperPoint is difficult to achieve real-time performance on the onboard system. Thirdly, almost all features of the SuperPoint are corner points, and the number of features is relatively low. And lastly, the descriptor of SuperPoint is too dense, which is not efficient. To overcome the noise of thermal images, we applied fixed pattern noise on various datasets to train our network. The first row shows original noise-free images from synthetic dataset, Kitty dataset, and thermal dataset. The bottom row shows corresponding non-uniform images after adding fixed pattern noise. To avoid features being only corner points, we applied pseudo-feature supervision strategies by combining the labels from handcrafted features and learned CNN filters. Here, we use SIFT method to generate some extra pseudo keypoint labels, which is marked by red circle. You can see the features are located on the large gradient areas. The green circles represent key points detected by ThermalPoint. You can see the features are mainly located on the corner areas. By combining labels from handcrafted features and learned CNN filters, we can obtain more robust feature extraction on thermal images. To solve the second limitation, we found that SuperPoint uses VGG-style shared encoder, which takes too much computation time. Therefore, it is not suitable for implementing on an onboard system. To solve this problem, we replace VGG-style encoder with MobileNet, which is more efficient. Since SuperPoint uses multi-cross entropy loss to extract the features, which can only select one feature for each patch. Also, since contrast of thermal images is not good, this loss is not suitable for thermal images and will result in a low number of features. Thus, to extract more features on thermal images, we use binary logistic loss, which will extract the feature on pixel level. Here is the loss equation that we used for ThermalPoint network. For feature detector loss, we use binary logistic loss to define if the pixel is a feature point. For descriptor loss, we use hinge loss to evaluate the similarity of the descriptors. To meet our real-time performance requirement, we propose a IMU-aided radiometric feature tracking method. Here are 4 advantages of feature tracking. Firstly, we directly make use of the full radiometric data from thermal images to find robust correspondences in consecutive frames. Secondly, we use the IMU pre-integration to provide feature transformation prior to overcome fast external movements. Thirdly, we perform patch alignment operation over the image scale space pyramid in a top-down manner to improve tracking performance. Fourthly, we employ an inverse compositional approach for faster computation. Also different from classical KLT, we apply local scaled sum of squared differences KLT to overcome the severe intensity changes. For thermal inertial bundle adjustment, we jointly minimize visual reprojection error terms of the tracked features, the IMU error term based on IMU pre-integration measurements, and the marginalization error within the sliding window. The first experiment I want to show is our feature detection performance with sudden photometric changes. We can easily find that deep learning-based method, ThermalPoint and SuperPoint, can robustly detect enough features even on the low contrast thermal images. However, the classical feature detectors like Harris, Goop feature, Orb, and SIFT struggle in the presence of sudden photometric change. We also performed the anti-noise comparison of different feature detectors in the presence of fixed pattern noise appearing as the vertical stripe. It can be seen that ThermalPoint extracts few features on the strap, while the other methods detect the many features. On the right, we use the repeatability score to evaluate the robustness of each method. If the repeatability score is high, the corresponding method has a good ability to overcoming photometric and viewpoint changes. It can be seen that ThermalPoint is the most repeatable under photometric and viewpoint changes. The reason behind this is that, different from classical detectors based on the gradient information, our deep learning-based method can learn anti-photometric and anti-noise abilities through a training process. In this video, we compare feature tracking results of ThermalPoint with famous SIFT method. It can be seen that ThermalPoint can detect and track significantly more stable features than SIFT method, even though the thermal images are noisy and dynamic. Because of the temperature difference between outdoor and indoor environments in the winter, it causes significant photometric changes on thermal images. However, we see that ThermalPoint can still track more features comparing with SIFT method. Here is a graph showing the average runtime performance of ThermalPoint. As we can see, ThermalPoint outperforms SIFT and SuperPoint. Compared with SuperPoint, our method improves the real-time performance by nearly 2 times. Here, we compare the accuracy of the odometry in the indoor environment. The picture on the left shows the accuracy comparison of the estimated trajectory in an indoor environment, where TP-TIO is shown in the blue trajectory. As we can see, the trajectory of our method is the closest to the red ground truth trajectory. On the right, we have a quantitative analysis of the ATE and RPE of the experiment. Our method reduces ATE by more than 6 times comparing with the second best approach. Here is the video showing the performance of different state estimation methods in an indoor environment. We handheld our device and walked 85 meters along the bridge and returned back to the same position, including purely rotation motion. Blue trajectory is TP-TIO and red trajectory is ground truth. The map is being built in real time by LiDAR odometry. As we can see at the end, TP-TIO has the smallest drift and returns to origin. This is the video showing our method outperforms LiDAR odometry when a heavy smoke is presented. When entering the smoke environment, LiDAR measurements degrades, while thermal images stays clear and provides useful information. You can see that even though the features are not sufficient, TP-TIO can still robustly estimate the eagle motion. In the end, we observe a smaller drift with our method comparing with LiDAR odometry. Finally, let me summarize our main contributions. First of all, we proposed the first tightly coupled deep thermal-inertial odometry algorithm, TP-TIO, combining learning features with visual inertial framework. Secondly, we proposed a new feature detection network, ThermalPoint, specifically tailored for producing key points on thermal images. We also proposed a new IMU-aided radiometric feature tracking method, establishing robust correspondences between consecutive frames. And lastly, we evaluating the accuracy, robustness, and real-time performance of TP-TIO from front-end to back-end in various environments. For future work, we need to add a loop closure module through ThermalPoint and correct accumulated drift for long-term navigation. Thank you for your watching.